Do you see the slides?
Yes.
Good, excellent. Okay. So, okay, this is the usual thing. I remind the students, let me know when you want to take an exam, and we have to discuss which particular topic you would like to present. I gave in here a list of possible subtopics of the class that you may choose. You may give sort of a presentation about it, and of course I will ask questions to stimulate the discussion. Okay, where are we? So today I would like to talk about, not sure if I'll have time to talk about both, two issues related to quantum transport. Quantum transport has a different meaning depending on the context in which you're working and you're interested in. It could be, as described here, simply semi-classical transport, but in a low-dimensional situation, in which quantum effects appear because of confinement of the carriers, say in inversion layers, in thin bodies, in quantum wires, in zero-dimensional transport, which is a funny way of saying it, in quantum dots, where quantum effects are clearly there. They have to be dealt with, but they do not affect transport directly in the sense that you don't have to, or you can get by without considering the wave-like nature of electrons and holes along the transport direction, roughly speaking. So this is one of the terms in which you find quantum transport cited in the literature, but it's really semi-classical transport in a reduced dimensionality. You end up in practice to solve a transport equation using a semi-classical Boltzmann equation in some form, but now the system is of reduced dimensionality. So you're dealing with a two-dimensional electron gas or one-dimensional electron gas. The second topic is quantum transport proper, in which quantum effects may be felt even along the transport direction. Again, I'm not sure if there is any general direct evidence that this is very important in normal quote-unquote devices. There are devices which have been designed based on starting from quantum properties, such as resonant tunneling diodes, that indeed are a little bit of the battle horse for various methods that have been employed to solve the problem. But in general, in a conventional device, I'm not sure if there is a direct evidence, unless you go to very low temperature, some particular situation like Bomaranov interference that is seen in at very low temperatures in metals and high mobility semiconductors. Nevertheless, there is a lot of work, and it's mainly driven by the fact that we're dealing now with low dimensionality systems in which atomistic simulation are required not only to deal with transport, but even to know what the structure looks like. So DFT is used, or even molecular dynamics for bigger system, or ab initio and not, to see what the structure looks like. So let me start with the first, let's call it a weak version of quantum transport, in which we're dealing with transport in cases in which the carriers, electrons, holes, are confined. For example, in inversion layers, this is the original situation. I'm actually not totally sure. I think that surfaces of liquid helium had been investigated even before silicon inversion layers. Quantum wells, which are important in high electron mobility transistors, so in high frequency devices, in lasers, in solid-state injection lasers. Nowadays, we're talking about FinFETs. We've been talking about fully depleted silicon on insulator devices, where you have very thin silicon bodies in which this sort of quantum confinement effects may begin to play a role. And now, of course, there is this very fashionable interest in two-dimensional materials, started from graphene, in which confinement is due to the ionic potentials themselves. that confine the carriers in two layers. Graphite is made up of several layers, which are bonded very weakly by van der Waals forces. The covalent bonds instead are very strong on a plane of each graphene layer. And the confinement of the electron is due to the ionic potentials rather than conduction band or valence band discontinuities that you have in these other situations. And then, of course, there are one-dimensional structures, starting from carbon nanotubes, nanowires. I haven't written here zero-dimensional structure like quantum dots, which are of particular interest in some photovoltaics applications and nowadays even in quantum computing. So the situation here is, as I said, weak quantum transport. Weak in a sense that there's not a big modification of the transport equation that we can use in practice. Remember that the Boltzmann equation is based on the fact, on some semi-classical assumption that you have a wave function, and you replace this wave function by a classical distribution function, assuming that indeed you do not have a plane wave, but you have a packet, and the packet has a broadening in momentum and real space, which in both cases is smaller than the energy or momentum scale of interest and of the length scale of interest. And so this is essentially, this arrow denotes semi-classical approximation, and we've gone through in painful details about what are the assumptions that you have to make in order to go to the Boltzmann equation. Here we do essentially the same, except for the fact that the wave function, rather than being a plane wave in 3 dimensions, is now a plane wave in a plane. This is a particular case that I use for 2-dimensional case. And then the electron probability is given by the square of some wave function along a confinement direction, the direction perpendicular to the silicon-silicon dioxide interface, or to all hetero interfaces that you may have in this situation, or to the plane of the 2-dimensional material. In this case, really, you don't do anything quantum in terms of transport, because you can easily convert your picture in a way which is totally analogous to what you've done in 3 dimensions, to write a semi-classical Boltzmann equation for transport in this 2-dimensional layer. The same thing can be done in 1 dimension if you deal with nanowires, nanotubes, in which now the plane wave would be just a plane wave in 1 direction, and the wave function will be confined in a cross-section of the device. So it's relatively weak. Transport is still treated semi-classically, although you have to account for some quantum mechanical effects. Now, the interest that I have in this is very practical. I want to drive two particular conclusions that explain why people are really interested in looking at 2-dimensional materials going beyond silicon. Essentially, I want to show that there are issues in scaling silicon devices, because when you go to very thin bodies, or even 1-dimensional situations, the scattering rates increase quite a bit. And that is driving the performance of devices which are so scaled, is driving it down. Now, whether these materials actually solve the problem remains to be seen. I'm actually a little bit skeptical from what I've seen so far, but it is the main reason why we're looking at alternative materials. I mean, people have been looking for alternative materials since the beginning. The main text that I would recommend if you're interested in the physical properties of 2-dimensional materials is this famous article by Alan Fowler, Frank Stern, and Tsuneya Ando. It's dated, it's quite old, but it's still extremely interesting and complete. And I don't think, except for 2-dimensional materials that at the time were not considered, the physics remains the same, and it's very, very actual. So the idea is, starting from silicon inversion layers, which historically is, if not the first, at least the second case in which this problem came out, you have a silicon inversion layer, This is your silicon dioxide. This is a p-type silicon, which is inverted by the application of a gate bias, which is sufficiently large to invert the surface of the p-type silicon and convert it into an n-type silicon. So you have an n channel, and this potential actually changes quite dramatically over a very short distance of the order of nanometers. And actually, if in a field of about a megavolt per centimeter in silicon, which is equivalent to a density of about 10 to the 13 electrons per square centimeter in inversion layer, the field is strong enough that the action happens over a 1 nanometer length scale. So electrons clearly now will be confined. You have to account for their wave-like nature. And the spectrum, which is continuum in a conduction band here, now will be discretized by the quantization effects that you have. If I'm correct, the first MOSFET in which these effects were seen was fabricated right at IBM in front of where my office used to be in the mid-60s. So the idea is you have the silicon conduction bands, considering an n-channel device. The equi-energy surfaces are given by these sketch, these 6 ellipsoids that are aligned along various directions. If this direction perpendicular to the silicon dioxide interface is the z direction, as I labeled here, then what you have, and say this is the vertical direction here, then you have essentially 2 different electron gases, one in which the mass along the direction, the z direction, is the heavy mass, the longitudinal mass, and 4 valleys in which the mass along the z direction is a small mass. I remind you, for silicon, the mass along this ellipsoid is about 0.9. Along this, in this ellipsoid, it's about 0.2. If you want to remember it is 0.91 and 0.19 for the two. These are good approximations to the values, which are not known to digits anyway. So what you do is you write your Schrödinger equation, as I will show you in more detail in a moment. You separate the variables. You get rid somehow of the coordinates, x and y coordinates in the plane. You still have a plane wave, and you're left with a one-dimensional Schrödinger equation, which gives you the eigenfunctions that represents the confinement of the electrons along the z direction. Excuse me. I'll give you a little better derivation in a minute. The problem has been solved historically. I think the first guy to solve it was actually Frank Stern in the mid-60s, using 3 different methods. One, which is the method we will describe in a minute, which is actually numerical, and it consists in solving self-consistently this one-dimensional Schrödinger equation and Poisson equation. I will give you details in a moment. Several approximations have been used. One is to approximate at high fields, to approximate the confining potential here in the depletion layer with a straight line, which is called the triangular well approximation. You have quasi-analytic solution. I say quasi, you can write them in closed form in terms of the Airy functions. The Airy functions are just a linear combination of the Bessel functions big J of plus or minus 1/3. You can get some closed form expressions for the energy levels that are formed and for the shape of the wave functions, the confined wave function. Frank Stern and Howard also proposed a variational method to solve the problem for the ground state by using I think they took hint from the shape of these functions, a wave function of this form, essentially a wave function which decays exponentially away from the interface and goes to 0 linearly close to the interface, and finding what is the value of the parameter b that determines the decay and the amplitude of the wave, which minimizes the energy of the electron system. Well, so these are useful approximations, particularly if you want to have some semi-quantitative estimates of various properties, sub-band separation, sub-band populations, and so on. By the way, I use the word sub-bands. Sub-band is just one of these eigenvalues, corresponds to the energy along the z direction, so to speak, in some parabolic band approximation, while you still have a continuum of states in the plane, as the electrons can move freely along the xy plane. And so they're essentially bands, but they're being divided into smaller bands, sub-bands, because of the quantization. So how do you derive that equation? I remind you what is the Schrödinger equation that we want to solve. I remind you about the usual method of separation of variables to solve partial differential equations when things are right, essentially when the terms that depend on position depend on a particular way, which you can factor. So you can solve this equation by separating the variables, expressing the unknown as a product of three functions which depend on separately on the three variables x, y, and z, and assuming that the potential that I have here varies only, depends only on the coordinate x. I'm not sure why I chose x here. Usually in the literature, the variable z is chosen, but it doesn't matter. So what you can do is you find that you separate this problem into three different ordinary differential equations. Now, each of them is similar. The two solutions, the two solutions of the two equations in a plane clearly will give you plane waves, which express the propagation of the electrons on the plane perpendicular to the direction x in this case. And this equation instead is the equation that we want to solve. I give you a lot of details. I hope you remember how to solve a system of ordinary differential equation. In general, it's very simple to do it when the equation has constant coefficients. Unfortunately, in our case, this is not so, because this coefficient, which is the coefficient that multiplies the variable x, which is our unknown or dependent variable, depends on the coordinate itself. So we have to do something different. But in general, this method instead can be used to solve these two equations in which there is nothing, that the coefficients are constant, do not depend on y or z, and you get plane waves. So I will not go through the details. I remind you here, and if you have time, please read it. When you solve an eigenvalue problem, a functional eigenvalue problem, the problem is given not just by the differential equation, but the boundary conditions are extremely important. I hope you remember what is the solution, the general solution of the Schrödinger equation in one dimension. This is the form of the problem that we have to solve now. This E actually is, again, the energy, so to speak, along the quantization direction. I'm using a rather rough, improper term, but I hope you understand what I mean. We've separated the energy into, into three pieces, and we're dealing with the energy in the quantized direction, which is this one. And of course, depending on the shape of the potential, as you all know from initial quantum mechanics classes that you should have taken, that the spectrum of this problem can be separated into three regions. I have a picture here for a general potential. This is an arbitrary thing. You will have a discrete spectrum. You may have a discrete spectrum if you find states whose energy is below the minimum potential on the asymptotes, either on the left or on the right. Then you have a singly degenerate continuum spectrum in the region between the potential on the left and on the right. And then you have a doubly degenerate spectrum that corresponds, the double degeneracy corresponds to waves propagating from the left to the right and vice versa, from the right to the left. And this is the general spectrum. Now I want to concentrate for now on the discrete spectrum. The potential that I do here, actually, we're interested in states which are in this range, which corresponds to the discrete spectrum in that picture. Up here, we will have a continuum spectrum of states. Okay. As I said, we can solve it in many ways, but the original, I think at least it was the original way in which Frank Stern solved it, was to discretize Schrödinger equation. So we start from our equation, we create a mesh, or we discretize the x-axis into elements, say, same length, uniform length, and then we express the second derivative in terms of finite differences, for example. So the second derivative of a particular point I in our mesh will be given by the difference between the derivative immediately to the right and immediately to the left. We take the difference between these two first derivatives divided by the interval, and we get the second derivative. In turn, each of these derivatives, I write index I plus 1/2, meaning that it's the derivative between the point I plus 1 and I. And so they are expressed here in terms of the same finite difference method. So if you plug these two expressions for the derivative to the right and to the left of our point I, we find that the second derivative at point I, which we drop now the dependence of a continuum variable because we've discretized the x-axis, and we simply use the index I to denote the value of the wave function at the point x sub I in our mesh, will be given simply by an expression which involves the evaluation of the wave function at 3 points. The point itself and then the point before and after. Okay, I guess this should be -1. I apologize. This comes from here. Oops. Okay. All right. So then the Schrödinger equation at the point I can be written in this particular way, where this parameter alpha just picks up all these coefficient algebra square over 2n divided by delta x square that you have, which is this expression that I gave over here. So you can write the value of the wave function at point I in terms of the value of the wave function immediately before and immediately after. This gives you an eigenvalue problem. If you write it in matrix form, assuming that the wave function vanishes at the initial and at the final point, so at the point 1 and the point n plus 1, so we want to find a solution in a system in which the wave function is forced to be 0 at those 2 points, then we have an eigenvalue problem, which can be written this way. It's a tridiagonal eigenvalue problem, so it's relatively easy to solve it, numerically in particular. And of course, the eigenvalues will give you the values of the energies in your inversion layers, in your quantum well, and the value of the wave functions give you a discrete representation of the wave function of the electron. Remember that we are working in some equivalent Hamiltonian model in which this will be the envelope wave function. So this is really the envelope wave function that we're dealing with. I will tell you later on, dealing with various methods used to deal with quantum transport in a strong sense. So when we really want to treat transport in a quantum mechanical way, how to, this system, I will rewrite it again, how it changes when we assume instead that we have an open system in which waves are injected from the left and from the right. So we are essentially in this continuum spectrum, either singly degenerate or doubly degenerate that we have in a transport situation. But now we're concentrated only in a discrete spectrum, and it's discrete simply because we found an eigenvalue problem. When we're dealing with a system which is open in a continuum region of the spectrum, rather than having an eigenvalue problem, we will have a linear system because the energy now is arbitrary. So we have to specify first the energy of the wave that it's injected, and then we find how it behaves inside the device. Here the energy is not specified. It comes out from the solutions of the eigenvalues of your eigenvalue problem. Okay, so this is how it was done. The problem is a little more complicated than that. This is the solution of, let me go back here, what is this envelope wave function along the z direction in this potential. Clearly you don't know the potential. So the problem is what is usually called a self-consistent Schrödinger-Poisson problem. You assume it's steady state, so no need to solve Maxwell's equation. Electrostatic is enough. You need to solve Poisson equation, which gives you this potential. Now, Poisson equation requires the knowledge of the charge that you have here. This is a p-type silicon, so we have, of course, the density due to the holes that you may have, a background density of the dopants that you have. These are treated in a way which is, well, the density of the dopant is fixed. The density of the holes can be obtained by using the usual bulk expression for the carrier density in a semiconductor. The problem is that the additional charge that you have here clearly is due to the charge of the electrons themselves. And the charge of the electrons clearly is due to the distribution of the electrons in the various subbands, depending on where the Fermi level is. So in fixed density or a bias, you know where the Fermi level is. You have to calculate the density of states in this two-dimensional electron gas, and the charge distribution along the z direction will be given by the sum of the square of these wave functions multiplied by the electron charge, adding up all of the population of all of the subbands that are populated. So your potential depends on the square of the wave functions that you have, and the wave function depends on the potential. So the problem has to be solved by iterations. Well, one way to solve it is iteration, but it's a self-consistent problem. So the way to do it is, the first thing, you have to calculate the density of states and the charge that you have in inversion layer. The good thing is that actually the determination of the Fermi level in 2 dimensions can be done analytically. In 3 dimensions, you cannot do it. The good thing is that if you use a purely parabolic band approximation, the density of states in a given subband is a constant. I remind you that the density of state is defined as the sum over all k states that you have in the plane. Now we're talking about the plane of the silicon-silicon dioxide interface. You count how many states, k states, you have at a given energy E. You sum over all the subbands that you have, and you get some number. Accounting for spin, you have a factor of 2 in front. This can be done analytically. You express the energy of the electrons in a given subband as the energy that the electron has this is a little messy. It's a plus over here, sorry. So this is the energy of the bottom of the subband, one of the eigenvalues that you have obtained by solving the one-dimensional Schrödinger equation, and then you add the energy of the oh no, I'm sorry, this is correct, with a plus sign. And then you have the energy of the electrons which are moving on the plane, which is the usual parabolic dispersion. Here I'm a little oversimplifying the problem for silicon. In silicon, we would have 2 different sets of expressions here, depending on which of the ellipsoids we're considering. For now, let's stick to, say, gallium arsenide, in which we have a unique mass. There is just some algebraic complications in which you have to deal with 2 different sets of Schrödinger equations, depending on what is the value of the mass for the ellipsoid that you're considering. But in a case in which you have an isotropic dispersion, then this can be done analytically. You get a density of states. Okay, that we can do also in 3 dimensions. You go to polar coordinates, and you can do this integration very easily, and you find that it's a constant. In 3D, there is an energy here. Here we don't have it. There is an extra k, so a square root of the energy, which we don't have here. So we have a constant. This is just a theta function, or the Heaviside step function. It tells you, of course, that the density of states in a subband mu is 0 when the energy is smaller than the bottom of that subband. It picks up in steps. Now, what is easier in 2D is to calculate the density. The density will be the same expression that we have for the density of states, but now, rather than simply counting the various states k that we have in a given energy, we count all the k states which are occupied. So we multiply this counting by the Fermi-Dirac equilibrium distribution function at a given temperature. This is simply done. Again, we go to polar coordinates. The integral over the angle just gives me 2 pi, which cancels one of the pi here. One of the leftover 2 cancels with this. This is the usual prefactor that we get when moving from the integration variable k to integration variable e. I have replaced the variable e with this expression, which is essentially the energy from the bottom of the subband and the Fermi level in units, in thermal units. And you get an integral, which is the same integral that you get to calculate the density in 3 dimensions, except that we do not have the square root of eta over here, which is what makes the integral solvable in a relatively easy way, and we get an expression for the density. So now we're ready. If we know, so the idea would be we start from some guess of the initial potential. the depletion approximation is typically what's used. We solve Schrodinger equation. We get a set of eigenvalues, is sub mu, which tell you which are the bottom of the subbands that you're dealing with. You compute the density, the electron density, and you determine what is the Fermi level. So depending on how you set the boundary conditions, you may say, I want to solve the problem for a fixed density, say 3 times 10 to the 12 electrons per square centimeter. Then you solve this system. You can do it by Newton methods, by bisection techniques and mixer techniques, and you can find what is the Fermi level that gives you the given density, knowing what the eigenvalues are. Having found that, you can calculate the charge density as a function of coordinate x. I don't know why I called it x again, z in the previous slide. And this is given simply by the density of electrons that you have in each subband, multiplied by the charge. I take E as a positive number, so I have a minus, and then, of course, the square of the wave function that you have obtained from solving Schrodinger equation. Having calculated the density, then you go and solve Poisson equation. Poisson equation will include a Hartree term, which will be the sum of the electron charge distribution that is given by this expression, the dopant charge, and the charge density of the holes. I think I have a slide in which I tell you what it is, but it's the usual bulk expression that you should be familiar with. In addition, there are other corrections. If you're dealing with the interface between two, in this case, dielectrics, silicon dioxide, that have a different dielectric constant, then you know that the potential will also be affected by an image charge, which is the image of the electron charge and all the charges that you have on this side. So in principle, you have also an image potential. We're also dealing with a many body system, although I formulated everything so far as if we were dealing with just the free electrons in this confining potential. That is actually the equivalent Hamiltonian for a single electron approximation in a many body system, with all of the approximations that we've seen at the beginning of the class. And so we know that in that potential, there should be also some corrections due to the exchange energy, although we're dealing with a single electron, I ignore spin. I've treated it just in the calculation of the density of states. Indeed, we should account also for the exchange effects that this many electron system has, as well as correlation. This we can do by some Hartree-Fock approximation. This is the usual problem, calculating the correlation energy. Frank Stern has done some numerical calculation accounting for exchange and correlation in some simple model, sort of equivalent to the linear density, local density approximation, and the image potential. In many cases, in most cases, these two effects sort of cancel. So ignoring them is, well, in ignoring them, we don't make a mortal sin. It's kind of okay, almost. So it simplifies the problem quite significantly. Exchange adds another complication because this depends on, so correlation exchange depend on the cubic root of the electron density. So there is an additional nonlinear term that you add. Self-consistency is not terribly complicated to add it, but the net effect, there's two effects sort of almost cancel. So typically, this is how you proceed. So you start from the depletion approximation. This is something that you should be familiar with from semiconductor physics, semiconductor device physics, whatever. So you use a depletion approximation at first for having fixed the density or having fixed a gate bias, whatever is the boundary condition you prefer. You can calculate the depletion width, and then you can calculate the total charge that you have, the density of the acceptors, the density of the electrons, density of the holes. For holes, you can follow the usual argument that the usual procedure that you follow in 3 dimensions, in which you calculate the density by counting the k-states. In this case, I have converted the integral already into an energy, which is why we have these factors in front, multiplied by the Fermi-Dirac distribution function. This is the same expression that we obtained before, as I showed you, except that now we have this complication of the square root of x here, the integration variable, And that's a nuisance because you cannot do this integration analytically. And you know that you have these Fermi-Dirac distribution functions or integrals, which are tabulated. There are dozens of articles in the literature which tell you if you don't want to calculate it numerically, the asymptotic expansions, the series expansions, interpolation functions, and so on. Anyway, at the end, you can calculate the density of holes, in particular if the holes are non-degenerate. And typically in this situation, if the p-type silicon is not degenerately doped, usually it's not, then you can use the simple Boltzmann approximation, and then the density of holes is simplified. And here clearly you have depletion, so you have no holes. So you can clearly use an expression which is much simpler. Again, this induces a nonlinearity in your problem. Anyway, this is a result that you can obtain. This is following exactly the Frank-Stearns procedure. There are some numerical issues if you use iteration. So you solve from a first guess. You guess the potential, you solve Schrödinger equation, you calculate the charge, you plug it back, solve Poisson equation, you get a new potential, you insert this new potential into Schrödinger equation, and you keep going. If you do it in this naive brute force method, usually you don't converge. You get instability, so there are techniques such as the under relaxation technique, in which instead of using the potential you obtain from Poisson equation, you use a mix of the potential you used in the previous iterations and the new potential. You mix them so that you slow down the process, but usually damp possible oscillations of the system. In quantum wells, this is even worse, because small asymmetries in a well and in a numerical solution that you get can lead to a well that oscillates back and forth with a positive or negative slope in the bottom of the well, and you never converge. So there are little tricks, numerical tricks that we can discuss, but I will not discuss here. And this, you see a result of these calculations. This is for silicon, so we have this Schrödinger equation. Sorry, let me go back to our equation that we have. This equation, we need to consider two groups. They're called ladders of eigenvalues that you will get. You have to solve this equation twice. Once using the effective mass, the heavy, the longitudinal mass, for the two ellipsoids, these two guys, if you are along the z direction, these are the two ellipsoids. And for these four-fold ellipsoids, four ellipsoids or one four-fold ellipsoid, you have to use the transverse mass, the smaller mass, as the mass along the quantization direction. And then you have to calculate the density of states. In this case, it would be just isotropic, as I described before. In this case, you have to use the geometric average of the longitudinal transverse mass, because the equienergy surfaces on the xy plane here will be ellipses. It's easy to do a transformation of variables and do that. So you have to you have to pay a little bit of an extra complication, price for the complication of this degeneracy of the minimum of the conduction band in silica. So you have to solve it twice. And where am I here? I was here. And so you see here the two different ladders. The ladder which has been obtained by using the heavy mass along the quantization direction. So these are the two-fold, the two ellipsoids whose longitudinal axis is along the quantization direction. They're called unprime essentially because they are the opposite of what I think is due again to Frank-Stearns. This notation is due to him. The ladder which gives eigenvalues which are higher in energy because the effective mass is smaller. They're due to, these are correspond to the four ellipsoids with the transverse mass along the quantization direction. They're called prime and unprime. This is just a convention. And you see that the prime values, let me look at here, which is zoomed in into a smaller region. The prime values are an energy which are smaller than the unprime values. So what you see here is the shape of the wave function, and I've displaced the zero of the wave function by the value of the subband energy, bottom of the subband energy that you have here. So you see the first eigenstate. Sorry, no, where is it? It's the blue one. The first eigenstate, the second one, which is this greenish guy, which is barely visible. Of course, the ground state doesn't have any node. The first excited state has one node. If you can barely see it, the second excited state has two nodes, these two guys over here, and so on. The primed have a high energy, so they are displaced up, and again, zero node, one node for this state, and so on. The Fermi level is set as zero here, so I've displaced everything down by setting the Fermi level to zero. And you see that your calculation of the density will have to be done by looking at what is the charge. So the occupation of these states, multiplying the square amplitude of this wave function by the electron charge, by the density of electrons in that subband, the square of the wave function, and you get the total charge. And I showed here, I believe this is the black line, is the total charge of the electrons. This red line is the whole charge, which is shown even better here. No, sorry, where is the whole charge? Oh, this guy, this is the whole charge. This is the potential. So holes is depleted, there's no density, you have only the density of electrons in inversion layer, but outside this, in this region, in this entire region here, you have neither electrons, which is this black line, nor holes, which is these dashed blue lines, and this is the purely the depletion region. Okay, any questions so far? This has been obtained by setting the density as boundary condition. So I fix the Fermi level by solving the equation that gives me the density versus Fermi level in a two-dimensional electron gas, setting the density to 10 to the 13 per square centimeter, which essentially is equivalent, if I remember correctly, is about 0.7 megavolts per centimeter at the interface. This is the field that you have for a density of 10 to the 18 acceptors per cubic centimeter. Okay, so let's get to the interesting part. Why did I discuss this? Why does it matter? So there are scaling laws. Professor Baccarani knows them very well, since he's one of the persons who formulated them first for sub-micron, quarter micron scaling. Now that we are even in a deep sub-10th micron, we're talking about nanometers now. I'm not sure what node we're in and what really the terminology, the name which is assigned to a particular node really means. I think we're down to probably the 1 nanometer node in experimental devices. The gate length is not really 1 nanometer, nor is the lithographic resolution or the half pitch. But anyway, whatever we are, we're down to tens of nanometers or less. And some scaling laws determine the way you have to shrink the device, not only horizontally in a plane, which is what you need in order to increase density and improve performance of the circuits, but also vertically. Essentially, when you zoom in, you have, or well, when you scale, you shrink everything. You have to shrink everything, keeping the aspect ratio more or less the same to avoid the set of problems which are known as short channel effects. Mainly, people are interested in the fact that if you don't scale properly, the device cannot be turned off properly. Then you have some off-state leakage. Power dissipation is the major issue that people are fighting with. So really, you do not want a large off-state leakage because the device is not really fully off. This requires scaling the thickness of whatever semiconducting layer or active layer of the device that you have, in addition to its length and width. And when you do that, there are some intrinsic effects which come from the fact that the electron-phonon interaction gains strength. And this is simply because the quantum confinement effects. This is something that no matter what you do, you cannot avoid. In addition, from a practical point of view, scattering with something which is not intrinsic, so let's call it extrinsic, which is the roughness that you I wouldn't say unavoidable, but in almost all cases you have at the interface between your semiconductor and whatever is confining your electrons inside the semiconducting layer, typically an insulator, be it silicon dioxide, aluminum oxide, whatever you have nowadays, boron nitride, hafnium oxide, whatever people are thinking of, these new materials that gain interest, you will have some deviations from ideality of the interface. And interface roughness is one of the most serious effects. And the fact that we're dealing with this problem, the fact that the electrons are squeezed into tighter and tighter spaces, has a big effect on the matrix element for your scattering processes. So let me go there in some detail. So we must scale thickness as we scale length. There are many papers that have been published studying in some semi-analytical way what is the scaling behavior of devices. So if you shrink the gate length, LG, of a device, how much does your body, your silicon body, I call by T sub s the thickness of the semiconductor, and by T sub x the thickness of the oxide or oxides that confine your layer. So think about silicon with silicon dioxide on top and bottom, or two different insulators top and bottom. In a fully depleted SOI, in which the bottom oxide does not contribute, the control of the channel potential and density by the gate is given uniquely by the top oxide, top gate. And a paper, essentially by my former colleague Jan Tower, says that if you want to have good electrostatic control, which means you want to shut off the device, the threshold does not deviate too much from what you would like to be. There's the famous problem of the threshold voltage roll off. When you scale the device improperly, the threshold voltage becomes, for a p-channel device, n-channel device, or a p-type, gets more and more negative, which is what you do not want, because you don't turn the device off. The rule of thumb is that if you set a gate length L sub g, the channel has to be the relation between the total thickness of the body and the dielectric thickness of the oxide. This is the equivalent thickness of the oxide measured in terms of the dielectric constant of the semiconductor. Okay, you must have that the gate length has to be bigger than 3.5 times the thickness, the total dielectric thickness of your body plus oxides. Put it the other way, if I put the 3.5 on as a denominator of Lg, I say that the total thickness of the semiconductor plus the oxides must be less or equal than the gate length divided by 3.5, which means that this total thickness has to be less than roughly 1.5 nanometer for a gate length of 5 nanometers. If you change the design of the device, and that's why the main reason why people are looking at devices which have more gate, so to speak, if you consider a multi-gate or a double gate, which is a device in which now also the bottom oxide has similar thickness and the gate can control the channel also from the bottom, you gain quite a bit, because now the field lines that extend from the gate do not propagate to the source, which is what you want to avoid, but the bottom gate will force them to go, so to speak, vertically. So you gain in a sense that now you can afford a body which is thicker than what you had in the past. Rather than 3.5, the magical factor now is 2.5. By the way, 3.5, 2.5, 1.5, these are not universal constants. These are rough numbers, more or less, okay? So now you can afford a total dielectric thickness of 2 nanometers. The problem now is that you have 2 dielectrics. There's a factor of 2 here. So the oxide has to shrink as well, or the dielectric constant of the dielectric thickness of the oxide has to shrink. And this is the reason why people are using high dielectric constant insulators, replacing silicon dioxide with silicon or hafnium silicates, oxide silicates, hafnium oxide purely, except for the fact that the interface you always get a little bit of native silicon dioxide. For other materials, people use a combination of various materials. For graphene, HBN. For TMDs, they use atomic layer deposition, often to deposit other high dielectric constant materials. But that's the reason why they're doing it. If you go to a one-dimensional geometry, now you have the gate, so a nanowire with all-around gate structure, then you get even a better situation. You can now afford a total, this is not a thickness anymore, I should call it the diameter of your nanowire, can be significantly, the condition, the restriction of that is significantly relaxed. You can talk about a 35 angstrom cross-section diameter for the total dielectric thickness. So this is the diameter of the nanowire and then the thickness of the shell of the oxide that you have around it. So the problem is that no matter what geometry you do, clearly having more gates, gates which are everywhere, that's why you have FinFETs, which has a gate on 3 sides, the omega gate transistor, the tri-gate. Now they're calling about multi-gate, multi-bridge, in which you have thin, very thin bodies with gates on the top and on the bottom. You can design a device so that you can relax the condition or have it to shrink the dimension of the body. But you have to do it anyway, regardless of what is this number, this coefficient that you use, what is the device, the design of your device, you have to shrink it anyway. And now let's look at what happens to the electron-phonon interaction if you're dealing with a two-dimensional electron gas. Let me remind you a little bit. These are some equations that we used in the past. The electron-phonon Hamiltonian is just given by the potential, which is caused by the change of the band structure, so to speak, for a non-polar interaction due to the presence of a phonon eta. Clearly, we'll have to specify at some point its wave vector q, and the electron density. So this is the Hamiltonian, the energy that we have that expresses the interaction between the electrons and the change of energy that you have due to the phonon. This may be a deformation potential. You may calculate this by using density functional theory, by calculating the change in the total energy when you displace the ions in a way which is corresponding to the propagation of a phonon, so the polarization vector of a phonon. And this can be expressed, as we did in some simplified forms during the deformation potential theorem, and very close to the band edges, in a form which is given by the amplitude of the phonon, which is this h bar factor divided by 2 rho omega, and then a coupling constant, which is a deformation potential, which has dimensions of electron volts per meters. It tells you how much the bottom of the conduction band on the top of the valence band, so the valence edge, the band edge, changes when you apply a strain. In this case would be a dilatation strain. Okay, so this will be the coupling constant, and then of course you have, as a result of the second quantization, canonical commutation rules for bosons and normalization of the states in Fock space, you have these Einstein's coefficients for absorption or emission of a phonon. For optical phonon, you have a similar thing. And this is the polar interaction instead, where we discussed this Froelich coupling constant. So this is something that we've discussed in the past. Regardless of what you use, for all sorts of phonons and type of interactions, polar or non-polar, you have a matrix element which has essentially some constant, which is roughly expressed, if we're looking at the rigid ion, the rigid pseudo-ion model, by the deformation potential, the polarization vector, the q vector, which is what we represent here. And then there is a matrix element which represents the overlap integral between the initial and the final wave function, modulated by the oscillation of the phonon field, if you wish. Now, if we consider a wave function which is given by a plane wave, a block wave, if you want, in a plane, multiplied by a function zeta, which is the wave function that we obtained from the self-consistent of the Schrödinger-Poisson problem we considered before, or if we're dealing with two-dimensional materials with the wave functions, the dependence of the wave function on the direction perpendicular to the plane of the layer, we have that the matrix element is proportional to this, whatever is the coupling constant and we have in front, and this changing depending on what is the phonon, the Q vector of the phonon, what is the type of interactions that we have, and then this matrix element. There is a standard trick. You see that here we are integrating over all possible phonon momenta of the phonons which we have in the z direction. This is assuming that the phonons are not quantized. Otherwise, because the confinement will also be affecting the phonons, although the boundary conditions are extremely complicated. But let's consider a silicon inversion layer or a material in which the insulators are very soft so that phonons can propagate also to the oxide in some form, so the reflections are very minor. And then you have the square of this overlap function. This is what happens using Fermi-Golden rule. And you sum over all this QZ, and this is the overlap between the initial and final wave functions multiplied by essentially the wave, the phonon wave. The standard trick is to express the square as write it as this term by this complex conjugate of the term itself. And of course, when you write it in these two ways, you have two integrals, and you write the integral, the dummy integration variable z as z prime now. So you have that this is equivalent to this form. Now you swap the integration over q with the integration over the spatial variable, and you get simply e to the iqz, which is coming from one of the two integrals here, and e to the minus iqz prime that comes on the other, the complex conjugate of this term. This integral can be done, it's the delta function. And so now you have an integral over z of the square of the wave function in one subband and in the other subband. Usually you can ignore the dependence on the parallel k vector on this wave function. If you're using parabolic band approximation, this dependence actually disappears. You have it if you're dealing with some full band calculations, for example. So at the end, you have that the electron phonon scattering rate depends on whatever is this coupling constant that we discussed before, times this form factor, which depends on the wave functions. Now, notice that in inversion layer, if you use, for example, the variational solution of the equation or the triangular well approximation, the square of a wave function grows with the density. The wave function is confined more and more strongly as the density increases, which one of these two terms, if you want, the first term over here, the normalization of this wave function doesn't matter because that's exactly the normalization condition. But you have now an extra term. And so it's the square of this extra term which gives you a factor which is proportional to the cubic root of the electron density, which is proportional to the cubic root of the gate bias or of the oxide field, or the interface field. This implies that the mobility will decrease as the density increases by the cubic root of the density. And this is indeed what it is observed experimentally, and it is well known. So the phonon limited mobility in an inversion layer increases with density. More interesting for the discussion that I have in mind is what happens when instead you're dealing with a quantum well, such as a fully depleted, the body of a fully depleted SOI, or if you do consider a double gate geometry or a nanosheet silicon devices like the nanosheet FETs that IBM has presented a couple of years ago, maybe 4, time flies. Now, this additional wave function, remember that this can be approximated like sines or cosines, depending on where you put the zero of your axis. But in any case, the normalization condition for the wave function is 1 over the square root of the width of the well. It enters with a square, so these extra terms give you a form factor that increases with 1 over the width of the layer. which means that the mobility decreases linearly with the width of the layer. And that's the problem. Go back to what we said before. This W is equivalent to the T sub S, the thickness of the semiconductor layer that we have. If we reduce the thickness of the layer, the mobility decreases. It's not just the mobility. Here I'm talking about mobility, but this is the general form of the matrix element for the electron-phonon interaction. So all electron-phonon processes at any energy will be modulated by this factor, either this one or this one, depending on the geometry you consider. So if you scale the thickness of your silicon body, the performance of the device will decrease because the scattering, inelastic scattering with phonon increases. The mobility, of course, you can calculate easily, but any other process will depend in the same way. So this is a serious issue. And the second issue, which is even more serious, perhaps I should stop here. Let me see, how many slides do I have? No, let me continue and let's have a break after I will have concluded this subject. The second issue is that at the interface between silicon and silicon dioxide, you have a rough interface. And this determines, this amounts to an additional scattering process. If you consider classically an electron coming in, a little particle, it can bounce off one of these steps that you might have. This might be a step because there is an additional silicon layer coming from the silicon dioxide. It protrudes inside the semiconductor. This roughness is sort of unavoidable, particularly when oxides became thin. As you know, the oxidation proceeds linearly at first because it's limited by the diffusion of oxygen through the layer of oxide. Sorry, it's limited by the interface chemistry, the speed at which silicon and oxygen recombine to form silicon dioxide. In later stages of the oxidation, when the oxide is thin, now you're limited by the diffusion of oxygen through the silicon dioxide layer that you've already formed. And this gives you a dependence of growth of the oxide, which grows like the square root of time. So in the early oxidation, which means thin oxides, the oxidation proceeds quickly. Quickly means that fluctuations also will be larger because you're more sensitive to the fluctuations of the amount of oxygen and how the interface chemistry happens, how the reaction happens. I recall that in the 90s, there was a report of record high mobility in a silicon inversion layer at low temperature, reported by a Russian group. And in the US and in Japan, nobody could match it. And the reason was in Japan and in the US, people were using thinner oxides, which had a rougher interface. In Russia, they were still using a technology of previous years in which the oxides were thinner. The growth was much slower and the interface was smoother. So it was an ironic situation in which we had better result using an older technology. But again, the devices were very long. So now the idea is that we can approximate this roughness. I will tell you a little bit about various models which have been proposed on atomistic grounds. And typically you characterize it by a power spectrum of whatever is the roughness here, which contains two variables. One is what is the average of the step height that you have. Typically it may be, since you can have one step, two steps, it can be anything in between, depending on how many steps of height 1 or 2 you have for one cell or two cells of silicon added or deleted from the interface. And then something which sometimes is called the average distance between two steps. It's really the autocorrelation distance of the steps. Now, let's call it the average distance between two steps, more or less. So you characterize this thing by these two parameters, and then you assume either a Gaussian or an exponential distribution power spectrum, which is typically for a Gaussian what you get from a total random cause of the steps. Experimentally, it seems that an exponential may be a little better, better agreement with the experimental data. Everything is a little tricky, both the measurements of the roughness as well as the characterization and calculation of the mobility. So I wouldn't come to a definite conclusion yet. But anyway, so the idea is that now what we consider happens at the interface are a variety of processes. First of all, consider a wave function, which was now quantized, one of the quantized wave functions zeta that we had. Let's assume that it extends into the oxide exponential, so it decays exponentially. This z goes negative, so this is the negative exponential. For negative z, it decays inside the oxide. Then, looking just how the wave function is shifted by this step, you can calculate a scattering matrix element, so to speak, which is just the overlap between a wave function and a wave function which is shifted. And this amounts, if you do some integration by parts of the integral, you get to what is a main effect that is responsible for interface scattering, which was due to the PN stands for Prangeny. Actually, it's Prangeny, they were French. It's called Prangeny in English. This was actually derived from what I mentioned earlier on, the oscillation of the roughness at the surface of liquid helium. So it's a completely different context, but that's where the model was originally derived, and it has been applied to the silicon-silicon dioxide interface by Ando. So for inversion layers, it depends on this. It can also be generalized. It can be shown that for some particular parabolic band approximations, it can be written in this particular form. The G stands for generalized Prangeny method, scattering rate, or matrix element, I should say, which is valid in thin bodies. Essentially, you see that the scattering is proportional to how much the energy of a subband changes as you change the width of the quantum well. View this as a quantum well. There is roughness at the other interface, and you have, as you move along the channel, variations of the width of the quantum well. A wider quantum well will depress the bottom of the subband, a narrower will increase it. So if you have fluctuations of this width, you have fluctuations at the bottom of the subband energy, and this contributes to a scattering process for the electron. It's interesting to notice that in inversion layers now, this derivative increases with density. You have the square of this derivative, so the mobility depends on the square root of the density. The scattering rate depends on the square of this matrix element. So the mobility in an inversion layer, due to scattering with the surface roughness, due to this particular process, the mobility decreases with the square of the density of the field, the normal field that you apply. In a quantum well, it's a disaster, because this now, you see that there is a cube of the width of the thin body, which means that this matrix element increases as the width of the body decreases with the cube of this width. So the mobility drops with a shrinking width of the body or thickness of the body with a 6th power of this quantity. So it's really a killer. The problem is the 6. It's extremely strong effect. So you change the thickness by a little bit and the effect grows enormously. There are other processes which in principle one should calculate. As you move the interface here at this step, you move the electron charge. This will cause a dipole of an electron charge missing here and added here, so there is a dipole. There is the image of this polarization dipole, and there is a shift also, the image potential that we mentioned before, because you're dealing with two dielectrics with different electric constants. They're also serious, they also go the wrong way, but they're all proportional to 1/W. So essentially the dependence will be comparable to what you have in inversion layers. The mobility will drop with the square of the width. So it is this element, this direct scattering at the step, which is a killer and kills the mobility in this dramatic way. And these are some results. What you see here are some calculations. These are from University of Bologna here. And you see the calculations that are done for the mobility in SOI devices, when you go down, for example, to 2.5 nanometers, your mobility as a function of density, or what's called the effective field, the confining field, drops on what is the universal mobility all the way down. So it's a real disaster. These are some calculations that Paco Gamiz from the University of Granada has done while he was at visiting my group at IBM, forget when it was, years ago, in a double gate, so in a quantum well, so to speak, in a silicon quantum well. If you go and look at the phonon limited mobility as a function of thickness, you see the various thicknesses, you see that the mobility, you go down to 1.5 nanometer, which is roughly the equivalent dielectric thickness, maybe a little bit bigger, but not much, if you want to compare silicon to many 2D materials that are of interest today. I find this is interesting. So the mobility is really depressed. You go from the 1500 that you have in bulk all the way down to about 500. However, we're still talking about 500. Now, consider the mobility, for example, for molybdenum that people have reported so far. I think that typically they are of the order of 100 is an optimistic estimate, has been obtained by someone. A calculation show a freestanding mobility for a freestanding layer of about 130. And if you put it on any substrate, the mobility is depressed additionally to the tens. So, okay, the problem is, and that's what you read in the literature, that interface roughness kills the mobility. And indeed, with some usual parameters for the average step height and correlation length that people are using, I forgot what we used. A lambda of about 1.5 nanometer and a delta of, I think it was 0.4 nanometer, so about that value. Then you see that by the time you get to 1.5 nanometer, now your mobility is depressed in the hundreds. And if you go to high field, you begin to see a depression caused by the field itself. Very small numbers, but again, the order of 100. So at 1.5, at 1 nanometer, okay, there is the 6 power. You can probably find something of the order of 40 or 50, which is still larger than what people measure in some transition metal like chalcogenide. So this is the interest that I have on discussing transport in lower dimensions, not so much because of the two-dimensional material, although we're working, everybody's working on those materials very actively, but because it is the main reason why people think that silicon is done. Again, they've been saying that for many decades. So I will stop here and then we'll conclude our real lectures with some discussion about strong quantum transport, or quantum in a strong sense. Okay, so let's take a 5-6 minutes break as usual. Any question, any comments so far? Anyone? Am I still alive? Am I still online? Do I exist?
We are still alive.
I exist. Good. Okay. So let's take a little break and I'll see you in 5-6 minutes. Anybody there? Can we start? Nobody?
Yes, we are here.
I'm here.
Good. Okay. So I guess you still have the slides, right? You see them?
Yes.
Good. Okay. So this is the last subject of the class that I want to discuss. Next time, I'm not sure exactly what we'll do, but I intend to give an overview, a review of the entire class, unless I don't make it to the end today. This is a very tough subject to discuss. So we talked a bit about quantum transport. We're more than a bit. We started from the Liouville-von Neumann equation, and we showed that under some approximations you can use a master form, a Boltzmann form of the collisional operator, which is what enters the Boltzmann transport equation. In general, scattering is a much trickier issue than that. So there are several approaches that have been used in the literature. The most popular one to deal with quantum transport is the non-equilibrium Green's function method, the NEGF. This is a method which was, if I know my literature correctly, actually the first time it was proposed by Julian Schwinger in I think 1950 or 51. Sylvester expanded it. Then, of course, it was independently developed by Keldysh and by Gordon Bain and Leon Kadanoff in the US and Keldysh in Russia, and has been popularized a lot by the Purdue group, Superior in particular. As a side personal remark, I had the pleasure of actually spending an entire day with Gordon Bain traveling through the Kona Highway in Maui. Somebody's got to do it. And we had a chance to talk about also this thing. And I remember his words. And he actually had said, even in the talk that he gave at that conference, I think it was December 2011 or 11 maybe, that the accounting correctly for realistic scattering processing realistically large devices is untreatable. It's true that hardware is improving, devices are shrinking. There are excellent calculations done, for example, for molecular devices in which this is done correctly. Nevertheless, it remains very challenging, but there is no free lunch. No method that we're going to talk about solves the problem of scattering in a satisfactory way in practice. So the idea is to start from the general 2 times Green's function. In second quantization form, you take the electron field, the Schrödinger field, you consider this quantity. The diagonal term, the R and R prime, T and T prime equal, is your density matrix. So here you're dealing with a 2-time object, so it's more general than the density matrix itself. And you develop, you go back to the Liouville-von Neumann equation and you see what you get. The math is extremely complicated. I'll try and give you a simple-minded approach. I found this paper, which is really nice, non-equilibrium Green's function for dummies in one particle formulation, mainly ballistic. It mentions what happens with the perturbation, but it's interesting to see the formulation of the problem in these terms and why it is so hard to deal with scattering in this formulation. It is fully equivalent to the density matrix for ballistic transport, but it has additional information, at least on the surface of it, about especially broadening. And it has information about what happens during a collision. Scattering is kind of intractable, except in a small system in 1 dimensions. Some attempts have been done with some approximations, but it remains an extremely hard problem to deal. And usually it is done in a simpler, using a simple model for the band structure. Typically it's using tight binding. Oops, another typo here that I hadn't seen. The idea is that you remember when we were talking about the Pauli master equation, how we consider only the diagonal terms because the representation was done in terms of traveling waves. So that really the diagonal elements in a ballistic case, it's all that matters. If you use a tight binding Hamiltonian, you pay the price of having to deal with the off-diagonal elements because it's only hopping from one side to the next that you get current. So just the choice of the representation of the basis functions that you want to use that complicates matters in some sense. There are lots of ways to deal with a density matrix. As I mentioned in the past, the argument is still going whether you really gain anything by considering different times here. If you consider equal time, you really deal with the density matrix, a row of R prime and T, single time. And then you have the semiconductor block equation, the Wigner function methods, the Master equations in various forms, whether it's strictly the Pauli or something which is augmented by some dissipation terms. And again, this deal with a one-time Green's function. It's almost diagonal, though, if you use the scattering states or the traveling wave representations. So its numerical implementation is a little simpler. You can treat dissipative scattering, as we've seen, either rigorously, if you account also for the off-diagonal elements or the density matrix, or for short devices, it's easier yet, because only the diagonal elements come in. The relevant information is almost diagonal when you use the scattering state representation. So my question is always, why do we need the complication on the GEF expressed in a local set of basis functions, which adds complications? Anyway, let me go back one moment to the one-dimensional ballistic quantum transport. I've shown an hour ago, the matrix that you get for your eigenvalue problems or for silicon in inversion layer. You get your potential discretized at V1, V2, Vn. This factor alpha, I remind you, is just the h bar squared divided by 2m delta x squared, where delta x is the discretization of your mesh. And then you formulate your Schrödinger single particle equivalent Schrödinger problem as an eigenvalue problem, which is similar to what you have in conventional quantum mechanics 101. If you open the system, so now you consider transport, so you assume that now waves are coming in. What you assume is you have waves of this form to the left and to the right of your counter. So to the left, you have an incoming wave. For simplicity, let's say that the amplitude of this wave is unity, so there's no coefficient in front here. K left is the K vector to the left. Let's consider just parabolic bands, single effective mass for now. And then you have a reflected component which travels backwards. And at the right, after you've gone through the device and you go into a region in which the potential is also constant, you have a plane wave which is propagating from the left to the right at an amplitude which is given by this transmission amplitude. And the square of this coefficient will give you the reflection probability. The square of this coefficient times the ratio of the outgoing and ingoing k vectors will give you the transmission probability. This should be well known, and the way you formulate the problem is discretizing in the same way. Notice that this matrix is exactly the same matrix in which I've added the diagonal minus e, bringing this term over here, but you have an inhomogeneous term. And the inhomogeneous term is what you get at the edge by simply considering that your wave function psi1, which is the first unknown, is related to the wave function, let's call it psi0 or plus psi minus 1, which is the wave function at the point which is immediately to the left of your device. You know what form it has, and then you can express the reflection coefficient in terms of the psi1. And that gives you plus an homogeneous term, an inhomogeneous term, which is what we have here. This alpha is the usual coefficient that we have here. And then we have this term, which simply tells you what is there is a problem with the subscript here, is the LaTeX, which doesn't know how to make this sub-zero superscript smaller. Anyway, this will be the form of the wave function that you have at the immediate left. This is what Bill Fransley actually, I think, was one of the first one to write the problem in this way. We call this term, plus this is the inhomogeneous term, and then you have a term which tells you what is the form of the wave function at the point -1, x -1, so immediately outside the device on the left. And we will call in general this thing with the quantity sigma sub L. Sometimes it's called the contact self-energy at the left. Really, it's nothing but the boundary condition that you have. So the difference between this system, which is the closed system, in which the wave function at x0 and xn+1 is considered to be 0, and here, where the form of the wave function at x0 or x -1, so immediately to the left and to the right of your device, so the simulated region, is assumed to be a plane wave, injected and reflected at the left or transmitted at the right. What you have is a conversion of your eigenvalue problem into a linear system. Indeed, you don't have an eigenvalue problem because the energy is arbitrary now. We are in a continuum region of the spectrum. You specify the energy, you solve your linear system, and you find what is the wave function which is propagating in a device. Once you have solved the wave function, you can go back to this expression here. From the ratio between psi0 and psi1, you get immediately the reflection coefficient, and then you can get the transmission coefficient from unitarity, or directly if you wish. In general, we can formulate the problem in terms of waves which are injected from the left and from the right with amplitude A left and A right, which, oops, what have I done here? Okay, to the left and to the right, they replace the unity coefficient that we have here. And then what you have is that you assume that the wave functions on the left side, outside the device, is given by a plane wave, injected, reflected, but now the coefficient depends also on what's injected from the right. Similarly, at the left, you crank the machinery, it's exactly the same thing. You express the boundary conditions at the left and at the right in terms of this form of the wave functions, and you end up with the linear system in which now you have two inhomogeneous terms which depend on how much you're injecting from the left, how much you're injecting from the right. You solve your system and you find the whole set of your eigenfunctions. I should say eigenfunction, wave functions for a given energy. And if you want to deal with transport, clearly now you will have to consider all these wave functions, consider the occupation of each of these wave functions given by the Fermi-Dirac equilibrium distribution of the left contact or the right contact, and then you have a solution of your ballistic problem. So it's a linear system in which you have these contact self-energies which enter your matrix, the energy, which is an independent variable that you specify, and typically you discretize it somehow and get the whole set of wave functions that you need. And then you have terms which express how much you're injecting. And this injection clearly would be determined by the Fermi-Dirac distributions of the left and the right contact. Okay, so this is what we call the I call the Fransley's method. And typically you rely on these contact self-energies. It's a fancy term, but really it's nothing but what are the boundary conditions that you're assuming, assuming that the potential is flat to the left and to the right of your the active region of the device that you're simulating. Okay, and this is how you go and calculate the transmission and reflection coefficients. Nothing particularly difficult here. The difficulty may come, and I've added this slide because I think it's worth emphasizing what happens when you have full bands, whether it be tight binding or pseudo potentials, DFT, for example. There are cases in which NEGAF has been used together with density functional theory. These self-energies become a mess. And that's because now you have to inject block functions which are expressed as sums of plane waves over all your G factors. So each wave that you're injecting is a combination of waves which depend on this G vector. And now the self-energies become matrices. These matrices possibly will have to be associated with states which are evanescent. In the case of a single band, you have just the propagating electrons. In the case of many band, you can inject electrons into many bands at a particular energy. And for some bands, you may be in a gap. You may be below the bottom of that subband. In this case, you have an evanescent wave. So you have to deal with the full, I don't go into details here, the full complex band structure of the system, of the contact, in order to express these particular self-energy matrices that enter. And your problem now becomes a mess because each of these terms, each of these elements in this matrix become blocks which have a rank of the number of G vectors that you're considering. For particular quantum system, the number of G vectors is large. It can be as large as 10,000. If you discretize the propagation along your device into 100 points, you realize that you have a system whose rank can approach or even exceed 1 million, depending on the number of G vectors you're assuming and the number of points. So it gets extremely complicated. And this is just something that I want to mention as why things get so complicated, even in a ballistic case. And why people are interested in a ballistic case, because there is a lot of information that you gain about the absolute maximum performance that the device may have. Okay, let's go back to quantum transport now in a non-ballistic case, although I'll use the ballistic case in a few cases. These are slides that I think I've already shown before. Remember that the most general object that we use is this Green's function that I've expressed before, which is the basic quantity considered by the non-equilibrium Green's function method. I will use the acronym MEGA for now. And actually, this is the reduced density matrix as we considered before, or the reduced Green's function. In equilibrium, we know how to deal with it. There is a strict analogy between quantum field theory and quantum statistical mechanics. The trick is a mathematical trick. In quantum field theory, this is called the propagator. Rather than being an ensemble average without a zero here that we should consider, this is the vacuum state of your system. There's no statistical mechanics here. You study the dynamics of the system, so everything evolves according to the evolution operator, e to the I, the Hamiltonian, the full Hamiltonian times time. If you convert the time to a temperature by doing a rotation of 90 degrees on a complex plane, you convert this into the Boltzmann factor, if you want, a statistical mechanics term, where beta is the inverse temperature. So with this rotation, you go from quantum field theory, it's called Euclidean quantum field theory, relativistic. This thing is called the propagator. Okay, now this becomes a Green's function. In equilibrium quantum statistical mechanics, this trick gives you this Green's function, which are sometimes called the Matsubara Green's functions. This is quote unquote easy in the sense that everything is known. There are books that describes this thing, and you can do equilibrium quantum statistical mechanics by essentially using the entire mathematical machinery which has been developed for quantum field theory, quantum electrodynamics, for example, to your case, to your many-body problem, and you get results using essentially the same mathematics, which is given by this trick. Of equilibrium is a totally different story. Again, we go into NEGEF, so we consider only the single particle Green's function, and we will deal now with this, which used to be our density matrix. We had a single time, and now we have two times if you want to deal with the general problem. So the complication is reduced somewhat, but still we have to see what is the equation that this object satisfies. Of course, the representation, as already implied in my previous comments, is very important. When we say diagonal, non-diagonal, well, it depends on the basis that we're using. Again, if you use a propagating wave, scattering states, traveling states, whatever you want to kill it, then the off-diagonal elements are sufficient to give you, in a ballistic case, if you're using a basis which is constituted by atomic orbitals, so a local set of bases, then clearly you're dealing with off-diagonal elements by definition, because that's what gives you the current. And the problem is that it gets ambiguous when you talk about coherence and diagonality. It gets a little confusing. Coherence is often defined in real space representation, and coherence in K-space may be completely different. So I'm not going to go discuss it into much more detail, but the natural representation that I prefer is using the eigenstates of the non-interacting device, including the potential, so the scattering states, because then in some cases that we will discuss, off-diagonal elements may be ignored if the device is sufficiently short. But in general, you have to do it. The off-diagonal elements are those that localize your wave packet. So you have a plane wave coming in the device. The scattering is weak. The packet, so scattering will essentially localize the packet by forming a linear superposition of states at various energies and wave vectors, so that you end up with a packet which is localized on a support which is given by the coherence length, roughly. If the device is sufficiently short, the idea is this happens way back into the drain where you don't care anymore. The current has been already set. If the device is long enough, you say this happens instantaneously, and now the packet is localized so strongly that you go back to semi-classical transport and use the Boltzmann transport equation. It's in between, which is the tricky part, okay? And that's where Negev is, as far as I know, the only way to deal with the system correctly, together with some density matrix approaches that account for dissipation in an explicit way. But I will not talk about them. So let's talk about Negev. What is the basic idea? Consider the system, the time-dependent Schrödinger equation. This is our eigenstate of those scattering eigenstates that I've just mentioned. This is the Hamiltonian, which includes the potential, but does not include any scattering. So the ballistic case. Add a perturbation. And this perturbation may be represented by a scattering potential entity V. I wrote V as a function of the density matrix itself. This term may be nonlinear. In electron-phonon interaction, for example, this object is really a non-local correction which accounts for the density matrix itself, the density, times the energy distribution, the change of the potential energy everywhere in a crystal caused by the presence of a phonon. So this object may be extremely messy. It's not just an external potential function of position. It's strongly dependent on the eigenfunctions, eigenstates themselves. So that's where the complication comes in. In any case, the Green's function idea is very simple. If we find the Green's function of this problem, and indeed if these are the unperturbed eigenstates or fields, if we look in second quantized form of our Schrödinger equation, looked at an equation of a field, if we find the wave function, the Green's function of the unperturbed system, when you add a perturbation, the Green's function, so the propagator in quantum field theoretical terms of the system with the interactions, with your electron phonon, electron impurity, electron, whatever it is, the interaction set of interaction you're considering, is given by, of course, the solution of the homogeneous problem plus the solution of the problem with the interaction potential itself. At steady state, it is usually convenient. So when you are in steady state, and that's typically what we will concentrate our attention, although in some cases, I think that transients are very important to see, for example, how fast a device turns on and off. But in any case, in steady state, people usually take the Fourier transform with respect to times of these objects. This is independent of time if you have an ergodic theorem, ergodic system. So we will consider this Green's function G0 of mu nu of V, we'll consider actually as G of V, assuming that we have some representation for it, whatever it is. So the idea is, in general, using turns out to be a Dyson equation where this depends on the Green's function itself. So it's an integral equation that has to be solved self-consistently. So the problems that we have to deal with, having given the general outline of what we want to do, is what do we do with contacts? In the ballistic case, I will show that actually the method is completely equivalent to the quantum transmitting boundary method that we've discussed before. What do we do to deal with ensemble average? This is actually introduced by the contact. It is the contacts that introduce many body effects via the boundary conditions, which are Fermi-Dirac distribution functions. And again, the crucial part will be what to do when V is not zero, when we introduce an interaction. So again, I'm adapting my slides from this nice paper, which is very, very simple. And it describes the system this way. Let's go just to the simple case of a single particle picture. And let's start dealing with the contacts by splitting the Hamiltonian into three pieces. A Hamiltonian of the left contact, let's call it 1. The right contact, let's call it 2. And then the device Hamiltonian, which is the Hamiltonian in which we have the variation of the potential that we've seen before. And then we have some interaction terms that tell us how the systems interact with contact 1 and how the systems interact with contact 2. And these are these subblocks tau 1 and tau 2. And then we have a vector for our wave functions, which is what is the state in contact 1, what is the state in contact 2, view this as a source, this is the drain, and what is the state inside the device itself. One can extend it to many dimensions with more than 2 contacts and so on in a similar way, but let's keep things simple. So we have split the subspaces into this way. One should say that if the tau are very strong, which is often the case, it's kind of, you don't gain much by rewriting the problem in this way. It's useful, such as in the Bardeen transfer Hamiltonian approach, when these tau are weak. So for example, if you're dealing with a quantum dot, which is weakly coupled to contacts via the tunneling barriers, then this representation is very useful and it leads to a numerical analysis which is simple. If this tau are strong, as you have in a normal device, then the problem remains complicated. But conceptually, it's something that one may think of on doing. Landauer used to say that he doesn't like this, that there's no way one can split a device, an entire system, into a contact and a device. Yet, I'm not sure what one can do without truncating the simulated region up to some point and then treating what's outside that simulated region in some quasi-equilibrium way to set the boundary condition. So I think it's a necessary evil to rewrite the problem into this form. So then let's define the Green's function of the entire system. This is our Green's function. Again, this is Schrödinger equation, a time-independent form of Schrödinger equation, okay? And this is the Green's function, the time-independent Schrödinger equation. In principle, if we account for the collisions, then we can do a little bit of algebra, and that's exactly the same equation that I wrote before. This equation written in different terms, the total wave function that you have in the presence of a perturbation V. This is a state which is the result of acting on the state psi with some operator, complicated, non-local, non-linear operator that may depend on G itself. That's a problem. And then this formally, this is how you would write your solution. What we have to understand, first of all, a matter of notation. Sometimes this G is called the retarded Green's function, and its Hermitian conjugate is typically called the advanced Green's function. It is common to consider the product of the GR and GA, that sandwich the outflux to the contact. This is sometimes called G lesser. I will not use that notation, but let's keep it simple and let's call it just G. understanding that it's the retarded Green's function. Again, in general, this terms V is a mess, and it depends on psi itself in a complicated way. So this is not, it looks simple, but first of all, you have to find G. Okay, not terribly complicated in a ballistic case, but solving this equation may be untreatable, actually, unsolvable in some realistic cases. Approximations will be needed. So this remains the main problem hanging over our head. Okay, so the basic idea is, and I want to show now, how do you use the Green's function to calculate the quantities of interest, the density and the current? Well, the probability current and the electrical current. So the idea is that all quantities of interest can be calculated from the device eigenstates. Using simple algebra, the equations that we wrote before, essentially this form of the equation, you can see that, where am I? You can see that you can calculate, for example, the states in the contacts by simple applications of your operators that are supposed to be known now of to the various states that you have. This is, for example, what you get from multiplying this by the second column, this by this. So the second column of your problem, you get this set of equations. And these little g's are the Green's function of the isolated contacts, G1 and G2. Here only G2 enters because I consider the state in a drain contact, in a contact 2. So they are the object that satisfy these. They should be known because these are flat potentials. They're the contacts. It's something that you can find relatively easily. Again, by using, so you can reformulate the problem in terms of these Green's functions. These should be little g's, I think, but whatever. And again, from the second column of this equation, you get some equations which tell you that the Green's function of the device, which is what you want to get in order to get all the information of the system, is just given by this expression. Is the inverse of the Hamiltonian of the device, having subtracted the self-energies, which are these objects. They depend on interaction of the device with the contacts, via these taus. And you see what I said before, if the taus are small, then you can use perturbation theory relatively easily to express the device Green's function and perturbations of the sigmas. If the sigma are strong, then the problem becomes more complicated. And that's what people usually do. What is important is to consider the spectral function. The spectral function is essentially the difference between the retarded and the advanced Green's function, or G minus the G dagger that we have here. In absence of perturbation, this is just diagonal. When you treat scattering, then of course the main thing that you will notice is this broadening of the dispersion. Here we see that for an energy E, the K vector that is associated with that energy is just given by the bare dispersion. This is h bar square K square divided by 2m for parabolic band approximations or a free electron. If you add scattering, clearly you will have to do, you will see a different thing. But in the case of the ballistic transport, again, I'm doing it ballistic because it's simple. When you deal with scattering, you will have to calculate this object accounting for scattering, but the formulation of the problem, so how to extract the density and the current in the presence of scattering, will be formally the same, except that every quantity which has a big A or some amplitude little a that is related to this quantity will be different. So the idea is that every information that we can get can be obtained from this quantity. Essentially, if we apply A to this state, remember this is a state which has been obtained by applying that operator, the complicated scattering operator to a state psi. So again, this is a complicated thing, but in principle, in a ballistic case, we know what A is. It's relatively simple. So we can get any information about the system using the spectral function, simply because you can show that defining the retarded and advanced wave functions from the application of the G and G dagger on the perturbation term, you find that this is actually the Green's function of your system. So now what we want to do is, we haven't dealt with contact yet, let's assume now that one contact, say contact 1, the left contact, I apologize for the R means retarded rather than right. So the contact 1 injects some states in some mode N. These may be subbands in a quantum wire, maybe subbands in an inversion layer, whatever it is, some mode. And the 1 simply refers to the contact. Then, if we insert this expression into the Schrödinger equation, we find some simple forms that let you define the density in a contact. The density in a contact is simply given by the density matrix of the states. This will be the states in your contact. So what you do is you simply integrate the spectral function of an energy, which is a sum over k, but converted into a sum over energies. And since the spectral density function is diagonal, is given by simply the delta function, you can get an expression for the density in a contact that depends on the Green's function of the device itself, the Fermi-Dirac distribution function in contact 1, mu1 is the chemical potential of the Fermi level. If the system is non-interacting, they are the same in contact 1, and then these matrices, which we can call this with another term. Typically, the terminology gamma is used for this object, gamma 1, which tells you what is the interaction between the contact and the device. And I think that indeed this is exactly, I anticipated myself, this is exactly the expression for this interaction terms. So we can find the density in a device and for the density injected from contact 1, similarly from contact 2, and adding them all up, we find what is the density in a device. So it is the Green's function in your device, which of course you know what it is in a ballistic case. This can be solved easily. These sigmas are nothing but the same sigmas that we used before, which is the quantum transmitting boundary method, which collapses into the Franz-Liszt method for the ballistic case for one band, into those complicated matrices that I just mentioned briefly and flashed in a slide when you do a multi-band, a full band calculations. But in principle, you know how to calculate this, and it's not particularly difficult to do it. So you are at a situation in which the density can be calculated by knowing what is the Green's function of your system, what are the sigmas that we already said we know how to calculate, and so what is gamma. So this is relatively simple. It's a complicated notation, but it's really nothing different from what we saw already in quantum transmitting boundary method or Franz-Liszt method in one dimension. For the probability current, it's a little tricky. In principle, you would have to use the calculate the velocity operator, which is not easily defined. So instead, we consider what happens in steady state. The occupation of each state has to be constant. We can write it inserting a completeness over here, and we can crank up a little bit of machinery by using the equations that we saw before. And at the end, we find that the change of the occupation of a state I is given by a sum of two terms that have to add up to 0. And we can interpret this as the probability current density due to contact 1, and this is the probability current density due to contact 2. So we can generalize it and say that the current density, the probability current density due to a contact I, is given by this expression, and if you multiply by the electric charge, you get the electrical current. And so you can write again, crank up the machinery. Again, it depends on what is the injection term from contact 2, for example, into contact 1. You can use the various relationships that we obtained before, relating the various Green's functions in the contact and in the device. And at the end, you find that the current density due to contact 2 injected into contact 1 is given by this expression. Again, these are simple quantities. They are scalars. If you're dealing, a matrix in which you don't have blocks, but you have simple scalar elements. If you're dealing with with a single band approximation, they become more complicated blocks with size or rank, which is given by the number of plane waves that you are considering, or in general, basis functions that you're using. Plane waves, if you're using pseudo-potentials, so the number of G vectors that you're using, or the number of atomic orbitals that you're using, for example, I guess 10 atomic orbitals if you use a tight binding with the sp3d5 s star approximation, which you're using up to the d orbitals. Again, if you use spin, then it will be twice as many. Okay, so it's a complicated notation, but it boils down to the quantum transmitting boundary method. The idea, of course, and the major complication, I mean, this is just an expression for the total current that we get. Okay, I will not go into details. The problem, and I show you some results. The problem, before I go into the detail, these results is the pros and cons. It's complicated, but mainly notationally if you're dealing with the ballistic. The real complication enters when you're dealing with scattering, so you're moving away from the ballistic regime. The good thing about this method is that it's rigorous and is generally valid, meaning it doesn't matter how big the device is, doesn't matter how strong the device, the scattering processes are, it's always valid. It gives you all sorts of information. The broadening of the states, you can extract current densities, you can extract the spectral composition of the various of the density, where I'll show you before. These are quantities, however, all of those that I mentioned, except for broadening, that you can get from a density matrix. And in a Pauli, in a master equation formulation with a dissipation term, you can also get broadening. So that's why there is still this ongoing controversy whether the Green's function gives you any more information than the density matrix, accounting for off-diagonal elements too. The not so good, but this is true for all methods, alas, is that if you're dealing with realistic, strong, non-local, Q-dependent scattering processes, solving this problem is daunting. I showed a case in which these operators, this V is actually resulting from the application to the state psi, so this already is an equation on psi, of a term which may depend on density, which depends on psi itself. So it's a complicated thing, and that's why using Q-dependent scattering processes, at some point, the integral equation that you get, this now becomes an integral equation, which is a Dyson type equation, involves, when you discretize it, the inversion of a large, very large, dense matrix, which is the worst situation you can encounter in linear algebra. It may even be nonlinear if you're accounting for electron-electron interaction. It's a dense matrix, it's large, the rank will be the number of basis functions that you have, which may be in tight binding, the number of atoms that you have times the number of orbitals that you assign to each atoms. In pseudo-potential, it's the number of G vectors that you have that can be tremendously large times the number of points that you use in discretizing your system. If you use 100 points for a one-dimensional simulation, say, of a silicon nanowire, use 100 points from source to drain in real space, and then you have 10,000 G vectors, then you have a 10,000 times 10 times 100, which is 10 to the 6. That's a million by million matrix that dense that you have to invert. Solving an eigenvalue problem of a rank a million is doable nowadays. Inverting a matrix is a much harder problem. It scales. I don't know if there are better algorithms, but in principle, it scales like a cube of the rank. So it's extremely hard. So typically, the idea is we use Q-independent processes because then you can essentially diagonalize this matrix. They become local interactions. Alternatively, people mock scattering processes with Buteker probes. A Buteker probe is a contact at a fixed bias that you attach to a side of your nanowire in the middle. This will create a potential, a change in the potential, which scatters the electrons, and then you can treat the problem essentially as if it were ballistic in the presence of this perturbing potential. And sometimes people use this trick to kind of mimic the effect of scattering, but really doesn't give you much of a quantitative information if you're interested in understanding what happens if you have electron-phonon interactions. Do polar interactions matter more than non-polar? You get no information about that. It is also, I may add, okay, I'm a little biased, less efficient than the quantum transmitting boundary method when you're dealing with a ballistic problem, because in the NeGEF you need ballistic NeGEF, which is a misnomer, I'll mention in a moment. You need all the states in a context. For Q2BM, you need a subspace of that, so it's way more efficient, although it's fully equivalent. Ballistic NeGEF is what you usually find in the literature. There are several papers which deal with scattering process with these approximations. There are significantly interesting papers that deal with scattering beyond these approximations, but in very small systems, typical molecular transistors. I have in mind the work which was done by Alessandro Pecchia and Aldo Di Carlo at University of Rome. For example, I think it's the first time that I saw a very interesting use of NeGEF for a small molecular transistors. The system is tiny, a few atoms. So that's why your matrix that you have to invert is not too large and you can do it. But typically people use ballistic NeGEF. Now, non-equilibrium means that you're interested in approach to equilibrium. So if you're dealing with a ballistic problem in which there's no such a thing, off equilibrium seems to be a little bit of a misnomer if attached to the word ballistic. So I don't like it. I mean, you're not going to have any approach to equilibrium if you're dealing with ballistic. So anyway, this is what you find usually in the literature. So that's all I have to say about NeGEF, just some results that I can show. This is from the NanoHub that Professor Gerard Klimek has built over the years at Purdue University. This is a ballistic MOSFET. What you see here is the local density of states energy resolved. So you see essentially the distribution of the electron occupation in real space as a function of energy. And you see the states in the source, the state in the drain. There's not going to be much tunneling current here. This is a device which is off. You see some tunneling inside the source channel region, inside the barrier, the virtual source barrier, but there's no current here. This is a relatively simple case. If you increase the gate bias and you reduce this barrier, then there are significant complications that you get that I will not go into. When you open the system and the current is large, getting convergence of any quantum transport calculations, even ballistic, is extremely hard. And that's because you don't have equilibrium here anymore. You lack the reflected states which give you the equilibrium charge density. Many electrons begin to flow. You distribute the charge instead of just in the source over the entire device. You end up with a density when the gate is really, the device is really on, gate bias very, very, very positive, with a lack of conservation of charge neutrality here, unless you do something to the boundary conditions. And that's why the Poisson equation usually here it's used with boundary conditions which are unphysical. They're Neumann boundary conditions. Essentially, you increase the Fermi level in order to retain charge neutrality, but this is clearly unphysical. So whatever. Strong scattering is really needed. This is a simulation instead for another program called NextNano, in which they deal with dissipation. So some approximate method to deal with scattering with optical phonons and phonon emission. In a quantum cascade laser, you inject the electrons. The electrons in this particular two wells can decay into the ground state, but the injection is faster than the decay rate. So at steady state, you build a population inversion. You have more states in the higher states and in the lower states, and this is clearly is a condition for initiating lasing. So these are calculations which have been done. I will mention a paper which deals with this situation by the group of Irena Nezevich at University of Wisconsin-Madison in relation to discussing the distribution function. Okay, so the next method that I want to mention is the method of the Wigner distribution functions. This is the same as the density matrix. Whether you go to some sort of Pauli or non-Pauli master equation, or whether you go to the Wigner function, is a matter of some sort of taste, preference, whatever. So the idea is to start from a density matrix, again, one time, because we're considering the Green's function but now at the same time, so it becomes a density matrix, at two positions. You write the two positions, R and R prime, instead of R and R prime, as two different values that depend on a sum or a difference, average, of two different positions, R and R prime. You integrate over this a second variable, and you define a Wigner function, sometimes called Wigner distribution function, although it doesn't have all the good properties of a probability distribution function. It can be negative. That's the main problem. You define this Fourier transform, which is not really a Fourier transform. It's a Fourier transform only on this variable. It's sometimes called the Wigner or Wigner-Weil transformation. This object, let's call it the Wigner function, you insert it into the Liouville-van Neumann equation in the presence of an external potential, no collisions yet, and you find an equation that is remarkably similar to the Boltzmann equation. This is for a homogeneous case, so you don't have a, sorry, this is just the velocity, so this is just the drift term that you have. It's remarkably similar to the Boltzmann transport equation, except that there is an interaction with the potential which is different from what you would have if you had here the field. So the field terms, which will be the term that you have dk dt, which is proportional to the acceleration of the field, is replaced by this integral expression, which is non-local, and this is sometimes called the quantum potential. This comes out from the commutator that you have in the Liouville-von Neumann equation. This has a lot of appeal for many people, because it says, boy, I'm getting an equation which is essentially semi-classical transport, as if it were, let's call it classical transport, except that I'm interact with the potential in a non-local way, and non-local in momentum space, which is actually the property, the mathematical property which permits you to deal with tunneling, for example, so with an effect that classically wouldn't have. So since it is so similar from a mathematical point of view, it is tempting to use one of the many methods that we solve to solve the Boltzmann transport equation, even moments, expansion into some orthogonal functions, Monte Carlo, to solve this quantum transport equation, ballistic. And indeed, all of these methods have been used by various people. They all have to deal with a little complication that is F can assume negative values, and that's where quantum interference is particularly important. So for example, if you use a Monte Carlo method, you have to use particles or quasi-particles or superparticles, whatever you want to call the walkers or the samplers that sample the distribution function. You have to give them negative weights in order to account for that. And this requires additional algorithms, splitting and merging of particles in particular situations with negative weights. And it may lead to instabilities in the problem, numerical instabilities. Nevertheless, it's appealing for this. It's analogy with semi-classical transport, with this non-local quantum potential. In a way, it is reminiscent of the Bohm formulation of quantum mechanics in terms of classical trajectories in this non-local quantum potential. And indeed, there are groups which have gone to Bohmian quantum mechanics to formulate quantum transport in this quasi-semi-classical framework. The problem is, not surprisingly, what is the effect of collisions? For many cases, people have assumed a master type of collisional operator, Boltzmann type. And this leads to what is called the Wigner-Boltzmann equation. There is a paper of a few years ago, again, which deals in superlattices and quantum cascade lasers by Irena Gnazevich's group. And they have derived the correct expression for the collisional operator that you get. Essentially, they had a lot of experience with the Limblad formulation of the dissipation formalism for the master equation, something I haven't talked about, and let's leave it there. But the collisional operator has a form which is really scary, and indeed, it's unless you do some drastic approximation, is unsolvable. So the bottom line is the Negev formulation has to deal with this problem, the inversion of a dense large matrix. The Wigner distribution, Wigner function approach has to deal with the form of the collision operator, which is a disaster from a numerical point of view. The Pauli master equation would have to deal with the off-diagonal elements too, which is, it gives you a problem which is of rank, which is rank of the square of the states that you have. So rather than, if you have 1,000 states, rather than a 1,000 by 1,000 scattering operator, the scattering operator now will be 1,000,000 by 1,000,000. So there's no free lunch. No matter what you do, at the end, you have to invoke some approximation to solve this problem. I think it's still the holy grail to find a way to express correctly scattering without excessively oversimplified approximations in quantum transport. No matter which formalisms you use, you bump into the same problem. Just to give you an idea, for an electron-phonon interaction, and this is in a Weak's coupling limit, that's the equation that you have to solve. I mean, it's you see, it's an integral equation. If you use a Monte Carlo method, it's way more complicated than the collisional operator of the Monte Carlo method itself. And the coupling with the phonon is the usual, I call it delta U before, is the usual coupling that we have, and it appears in front of this expression. Okay, so even in this case, it's tricky, yet people are still using it, and I think that there are satellite conferences which are held just on the Green's function, on the Wigner function method. This is an example that I took from Mitzi's work at Technical University of Vienna of a resonant tunneling diode in which you have a gallium arsenide, aluminum gallium arsenide system with a quantum well, and you can have resonant tunneling between the two, and you can use the Wigner functions to look at the current, and this is the Wigner function in real space along the x direction, and here you have the k vector, the f, x, and k that you have for this one-dimensional problem, and you see the tunneling process that occurs here. Okay, pros and cons. It's good because it provides an intuitive, so to speak, generalization of semi-classical transport if you're willing to accept negative probabilities. As I said, solution methods which are being used to solve the Boltzmann transport equation can be used for the Wigner function, for example, Monte Carlo with negative weights. Not so good. In addition to some possible numerical instabilities that you may have from the negative values that you have to use, and the fact that the collision operator is unmanageable, and usually one gets this Wigner-Boltzmann equation, but there's no rigorous justification. I recall a visit by Carlo Iacoboni at IBM for a summer, I forget when. He worked with Peter Price trying to formulate in some rigorous way the collisional operator in the Wigner function method, and they ended up giving up at the time. There is another issue, which is, I'm not sure I understand it, understand the status of this issue. Professor Fausto Rossi, now at Polytechnic in Turin, but I think the work started when he was at Marburg, working with Tilman Kuhn, showed that you can get unphysical solutions when you solve the Wigner function problem at steady state. And you can get some physical states. And if you set the task of solving the system numerically, at some point you don't really know what is physical, what is not physical. So there's this lack of uniqueness of the solution, and some solutions exist that aren't physical. If I understand correctly, a postdoc of mine, a research scientist working here at UT Dallas, a brilliant guy called Dr. Van de Put, has worked on the Wigner function itself, and he assures me that the problem can be solved, but you pay a heavy price. You have to solve the full time-dependent system, even at steady state. And introduce the boundary condition as a time-dependent problem. And then that solves the issue. So I'm not sure, perhaps some of you know better than I do what is the situation with this problem. These were very interesting papers, and the solution is not so obvious. So you have to struggle with this. Again, I'm not an expert on the Wigner function. I haven't followed the recent literature. I don't know whether a solution by keeping the problem in a steady state exists. Otherwise, you have to do some trickery to skim away the unphysical solutions. I will stop here. The rest is just something that we'll talk next time. I will want to go back to the Pauli master equation and show in particular what we've done using empirical pseudopotentials to give you some idea about the research that we have going on, some results related to scattering, even using the Pauli master equation in silicon nanowires and graphene nanoribbon field effect transistors, so in one-dimensional systems, but treated three-dimensional in terms of the Poisson equation, and looking at the effects of these collisional processes on their transport, on the current of the device. And there's some interesting thing. For example, in a graphene nanoribbon, the one carbon vacancy at the edge of the transistor can degrade the current very significantly. So if you are a believer on graphene electronics, you have to open a gap. Typically, defining nanoribbons is one way to open a gap. They have to be narrow in order to have a gap good enough, large enough to do complementary logic, CMOS. So it's kind of bad news. For silicon nanowires, instead, the role of electron-phonon interaction is very strong. We have results related to bulk phonons. For small nanowires, that's a bad approximation. And indeed, dealing with confined phonons is the next thing that we have in a to-do list, actually. We're working on it as we speak. But so this is something that we'll do next time, concluding with a brief review of the entire class. So, are there any questions, any comments? This is our subject, so I wouldn't be surprised if...
I have several.
All right, that's good. Somebody. Yes, please.
First of all, I have a question, an explanation. When you introduce the various methods, the green functions, and compare with the density matrix approach, I don't understand. You said that the density matrix, you have a single time instead of t and t prime.
Yes.
Now at this point, I don't understand the following. In the green functions, you have t and t prime, and then in a stationary problem, the green function depends on t minus t prime, of course.
Yes.
And then you take the Fourier transform with respect to t minus t prime, which is the energy, like we interpret as the energy.
Yes.
So you get eventually the energy spectrum.
Yes.
Current density, the electron density, whatever, resolved in energy. Now I don't understand, with the density matrix approach, you don't get the same information because you have only one time?
That's a question. I claim you do. It depends. I mean, you have the density matrix, you solve for it. So I'm skimming towards the last results of the we're getting now. Okay, look at this picture. This is exactly the same picture that you get from McGeff. Okay, This is the local density of state energy result. You have the density matrix. Okay, you have a single time, but you can still express the density matrix in the basis of the eigenfunctions of the unperturbed Hamiltonian. And so you get exactly the same spectral information that you get from Negev. So this is where I say there is a controversy. The typical antagonist that I have is Professor Dave Ferry. We keep bumping our heads on many issues. The Copenhagen interpretation too is against it. I'm a Copenhagen bigot. But one of the things he says is, oh yeah, with the Negev you really get more information. I'm not sure that at the end you cannot extract the same information from the density matrix. In a way, you suggested a solution. Okay, I have one time. I take the Fourier transform with respect to that time, right? So I don't know. There is a controversy. People are arguing back and forth, but pictures like this one, right? Okay, you get exactly the same information that you get from Negev, with one exception, which is the broadening of the states. We don't get the broadening. We will need the off-diagonal elements. These are other pictures. Look at a nanowire FET, and these are the same pictures from before. This is a nanowire, a nanoribbon FETs with the defect scattering, and you see the effect of scattering, you see a spectral decomposition of these states. So I claim that you do a lot of well, I shouldn't say a lot of extra work. At the end, it probably boils down to the same, because scattering controls everything in terms of the CPU time you need. But I don't think that it makes such a big difference.
In any case, you can get the energy spectra as well with the
exactly.
That's it.
Exactly.
And with the Wigner approach, you get the information on the energy with the pseudo Fourier transform with respect to K to the
Yes, indeed. You can show the picture, right, of Mitz's work, and where is it? Somewhere. Here it is, right? You get the K information.
So there is the K information, which is eventually equivalent to the energy, but this is a sort of Fourier transform with respect to the spatial variable.
I'm not sure. I'm not sure if you're not in steady state, maybe there is something. Not in steady state, you really have a retardation. You may have a retardation effect. So I don't know if that, typically you talk about retardation in electrodynamics. I don't know if it matters in this context. So you have a perturbation due to a phonon now, and you feel it later. I don't know. This is something that in steady state you ignore, right? Use the ergodic theorem and say, well, it doesn't matter when the phonon was there. So maybe there is something there, but I've not seen any conclusive argument that I agree with that says, you can't get this information from the density matrix. Only the Green's function can give it to you. I cannot tell you anything. Give you one case in which this is true. Okay.
Well, another question about collisions. Okay, you said that the problem with the Green function is when we have a Q-dependent collision.
Yes.
But actually, if you consider phonons, which I mean both acoustic and optical phonons, they work reasonably well, I guess, because you don't have a strong Q-dependence with phonons. Is that right?
If you assume for acoustic phonons, if you assume parabolic bands and elastic. Collisions. If you drop the elastic approximation, that at low temperature is not good anymore, then you have a Q-dependent process. If you go to any atomistic modeling, then the matrix elements depend on K minus K prime, on the difference between initial and final wave vectors. So they depend on Q. Any sort of Coulomb interactions, Fröhlich scattering, impurity scattering, they depend on Q. And then things are non-local. I know that some people have done some good work trying to bypass the difficulty, but it's complicated anyway. So that's why I wrote somewhere here that usually you do some approximation. With Q-independent processes, indeed, I know simulations of transporting nanowires with a NEGF with inelastic optical phonon scattering, but
Yeah,
acoustic phonons, they have to be done as usual. But for the phonon, acoustic phonons, they use the elastic approximation. This makes it interaction local, and then you diagonalize the matrix, and then you can invert it much easily, of course.
Okay. And with the Wigner function, I assume there are a lot of comparisons between the Wigner function approach and the green function approach with comparable approximations for the collision terms. I mean, are there relative equivalent approximations in the green function approach equivalent to the diagonal, or keeping the diagonal term only in the green functions?
Yeah, I was looking, preparing these lectures, I was looking at some recent papers about that. I forget which paper, might have been this one. They say actually that your assumption that there is a lot of work in comparing this method is not so normal. There's not much around. And that's, I think it's due to a practical thing. I don't think there are many places where they have both a good NEGF and a good Wigner function program, computer program. One would have to do some collaboration. I think like some inter-university, inter-institutions collaborations, like what we did years ago with Jack Hickman about the Monte Carlo, right? Comparing all the Monte Carlo programs around the world. One could do the same thing. That's actually would be a very good idea. I think that there is a Wigner workshop organized by Dave Ferry, I think, maybe Joseph Weinbach too, a satellite to the IWCN this year, that however is virtual only, I think, usual issue. But it would be good to talk to various Wigner function people and NEGF people and see if there can be, they can draw a comparison. And maybe even the master equation people, the density matrix people, that could do it.
But actually, there aren't many groups working on Wigner functions around in the world, except Vienna.
Oh, yes, there are lots of groups. Yeah, the only case I'm surprised is Bill Fransley, who has abandoned them for some reason. But I don't know why. I asked him, but I didn't get a straight answer. So, but yes, there is a lot of activity. The good thing about Wigner functions is that people who work on Wigner functions usually know what they're doing because it's not commonly available. People who use NEGF, boy, NEGF is available in as packages, and sometimes you find papers in which it's clear that they have no idea what they're doing. They do NEGF, but who knows what they really did. So I would trust in some sense a comparison with the Wigner side of the comparison. People usually know what they're doing, that they're good. NEGF, there are good people too, of course, and one should ask those. So I'm not aware of any direct comparison. I mean, the resonant tunneling diode has been dissected so many times that I'm sure one can find something. Okay, something along those lines. For example, the good thing about this plot is that they find something that Roger Lake keeps hammering, the fact that actually scattering increases the valley current because it opens a new channel for scattering off resonance. So that's something good that the Wigner function predicts. I think we also find it in with the Pauli master equation, except that we get a strong bistability. That's the other issue. With resonant tunneling diode, you go into the other controversy, is the bistability, the oscillation, an artifact, a numerical artifact, or is it really a real effect? So, again. What's the next question?
Okay.
You done?
Can be enough. Thank you.
Okay. Any other questions from anybody else?
But maybe George will have many more questions.
George, actually, I would have to study before asking questions.
You know, you probably would have more questions on the lecture I gave last week. I was relieved
Unfortunately, I
that you
missed
didn't
it.
attend because I was talking about your work. So I probably brutalized it and massacred, and you were not there to spot my errors. So I had a free pass.
Well, I don't think you did any error.
I don't know. It's about the spurious velocity overshoot and those things that
Oh,
your
well,
models for the
that
relaxation
is a
rates.
detail, is a specific feature of the hydrodynamic model.
Yes. Okay. If
Okay,
not,
so
next week I will
thank
finish
you.
up. Thank you. Next week I will finish up with what I already flashed, the slides I flashed, and then probably give a brief review and re-summarize what we have done. It will not be a full 3 hours thing. It will be much shorter than that. Okay. Thank you very much.
Bye-bye.
Bye-bye. Have a good weekend.
Bye. Bye.
Thank
Bye.
you.
Bye.
Bye-bye.
Bye-bye. Thank you.